thanks everyone for coming, especially committee members here. This is my PhD thesis. The title is Alfvén wave turbulence and structures in the solar wind, insight from Parker Solar Probe. So, this is the first publications that will be discussed in this thesis. I first want to send an acknowledgement to, first of all, our group members, and the most important trace list underscore over there, and also to the committee members, Professor Vasilis Angelopoulos, Professor Hao Cao, Professor Paulavis, also Committee Chair Professor Marco Valli, also some important collaborators and some friends. And this is included in my dissertation, it's the dedication. So I want to name my thesis as magnetic nonlinear connection with some various reasons. I also want to send thanks to both my mother, my grandparents, and my wife who's sitting over there. Okay, so let's get started. This is the outline of this presentation. I will start with the introduction, and I will discuss the structures that I found in the solar wind, and also all the new phenomena from Parker Solar Probe about the Alfvén wave turbulence in the heliosphere, with three parts. First part being understanding the mode conversion of linear MHD modes, and then the 1OF energy containment range in the turbulence from Parker Solar Probe data, and this newly found 3 minutes oscillation in upper corner from PSB data. And then I'll discuss the conclusions and future work. Actually, I want to know whether I'm able to be here online. Can I?
What do you want to do?
I just wondering whether I can be heard online.
Yeah, we hear you.
Yeah. Okay. Thanks, Ben.
Perfect.
Okay, so let's move into the introduction. So first I will discuss the structure of the sun. Let's get started. Do I have a physical here? Like this. Okay, so this is the structure of any stellar object, any stars. For our sun, it's something like this. You have the radiation zone from the core, from 0.2 solar radii to 0.7 solar radii. And then you have a convection zone from 0.7 solar radii to the solar surface. If the sun, if the star is more massive, the convective zone will be reversed and be put inside the star. But however, some claim that the convection zone doesn't exist at all. And the outer layer of this object, the outer layer of the star will be the radiation zone. So the difference between the radiation zone and convective zone is that the energy will be transported through convection in the convection zone. So due to the buoyancy of the plasma, it will float above if there's if it's hotter than the surroundings, and it will fall downwards if it's cooler than surroundings, and that will create the convection. However, in the radiation zone, the plasma cannot basically move, so the energy is primarily transported with radiation. So our sun is typical this kind of star. We have a convection zone for our sun specifically is 0.7 solar radii to the surface. So here is the structure of our sun. We start from the core where the fusion actually happens, and then we have a radiative zone, and then there's a tachocline. It's a Greek word, and tacho means speed, and climb means the slope. So tachocline means the surface where below, in the radiative zone, the sun is rotating like a solid body, but above the convective zone, the sun will have the differential rotation, and that's why it's called tachocline, because the rotation speed changed quite a lot at the surface. And above, we have the convective zone, and on the top of the convective zone, we have the outer boundary of the sun, which is called the photosphere, where it emits the photons that you can see from the Earth. And on the photosphere, we have all of these phenomena. For example, the sunspot. Sunspot, we have umbra, and granule. The granulation is a very interesting phenomena on the surface of the sun. You have all of this very small scale structures that is pretty much 1.5 million meters that's happening all the time. And if you go even above in altitude, you reach the temperature minimum, which in physics defines the outer boundary of the sun. And then above the temperature minimum, because the density drops so quickly, and it cannot compensate the energy that's being transported from below, from lower layers to upper layers, and therefore the temperature has to rise to have more radiative cooling, and that creates the chromosphere.
Hey, Zesen, can I ask you a question?
Yeah.
We have 2 hours
until
10 o'clock. And I'm wondering if time your presentation to be like less than an hour or so, so that we can have some time at the end for discussion.
Okay, I will be quick. Okay, so there are all of this.
It's introductory stuff, so maybe quickly.
Okay, so it go above you reach the transition region, and then the temperature become even higher, and then you reach the corona where the temperature become median degree, and then the outer boundary of corona creates the solar wind. Okay, and this is the temperature profile of the solar atmosphere. You have the temperature minimum here and temperature rising chromosphere, and then rise very rapidly in the transition region and reach a median degree in the corona. And this is our solar cycle 25. It's very active. This is the sunspot that created the largest event in 20 years, a few weeks ago. Sunspot AR 3664. And this is the solar corona, what solar corona looks like in minimum. The reason I want to introduce this because a part of my work is to identify structures using in situ data from Parker Solar Probe. So I want to introduce what solar corona looks like. And this is what solar corona looks like in solar minimum. You have the polar plumes, and you have the helmet streamer in the ecliptic plane. And this is an expanded view. You have streamer here, and you have pseudo streamer here. A pseudo streamer is a streamer where on both sides, the magnetic polarity is the same. A streamer on both sides, the magnetic polarity is different. However, this is solar corona in maximum. This is solar corona actually last year. You see, compared to solar minimum, there are corona holes everywhere. All of these plumes are from corona holes, and you have streamer belt everywhere. The main difference is that this is solar maximum that we are the solar condition now. Solar probe is actually traveling somewhere here. The closest approach of solar probe is actually somewhere around here. It's on 10 solar radii, so it's pretty close. We're actually touching what we are seeing in solar eclipse. For example, like this plumes, and also there's a CME here. You can notice. So our next part is to discuss what is Parker Solar Probe. So this is for Parker Solar Probe. You have 4 primary instrument suites. One is the fields. You measure the magnetic fields and electric field. You have the sweep instrument suite, which measure the ions, electrons, and other particles, and other heavier ions as ICs for measuring the energy of particles, and whisper, which is the imager. And this is the orbit of Parker Solar Probe as of 2 days ago. It has finished its 19th encounter. So the closest approach is about 11.4 solar radii as of just now. And this is the orbit design of Solar Probe. Here is the orbit of Solar Probe, which is this white and greenish line. You can see moves actually pretty quickly, and this is in solar inertial frame. And this is the orbit of Solar Probe in the co-rotating frame, because as we know, the sun has a 27 days rotation period in the ecliptic plane. So it is subtracted from the point of view of the sun. This is the orbit of Solar Probe. You can see as Solar Probe approach the sun among perihelion, there's this fast radial scan phase. So basically, it's co-rotating sun, so you're continuously measuring the same plasma for an extended period of time. And this is the orbit of Solar Probe in 3D. You see, it's pretty much in the ecliptic plane for the same orbit, so it's not moving that much in latitude. That's very important. I will discuss that later. And why the Solar Probe actually matters? Because, or why people claim that Solar Probe is actually touching the sun's atmosphere? Because the outer boundary of the solar corona, or the outer boundary of the solar atmosphere, is defined by this radius, which is often considered to be at 15 solar radii. It's called the Alfvén surface. The Alfvén surface is the surface where the solar wind speed become larger than the Alfvén speed. And because of that, and because the primary information carrier in solar wind plasma is Alfvén wave, above this layer, information or the backward propagating Alfvén wave cannot reach the sun. So this boundary is actually defined as a causal disconnection from the solar surface. So that's the natural boundary of the solar corona. So below that, information can propagate both ways and reach back to the corona, but above that, information can only propagate outwards. That's how the boundary is defined. And the solar probe mission is designed to touch down into the solar, the outer boundary of the solar atmosphere. And as of now, it's pretty much here. So actually, as of 2021, solar probe has been providing continuous measurement of sub-Alfvénic solar wind, which is solar corona for now is already for 3 years. Okay, this is what solar wind looks like for solar cycle 22, 23, and 24 here. And solar minimum, you have fast solar wind in the polar region, which can reach often 750 kilometers per second. And the magnetic field of the sun is pretty much a dipole, so you have a unipolarity on both poles. And as the sun becomes more active in solar maximum, which is the sun now, the magnetic field become more complex. You have heliospheric currency everywhere, and the polarity of the magnetic field will change quite a lot, and the solar wind everywhere change quite a lot. This is especially so, and this is also the case for solar probe in the ecliptic plane, because on the ecliptic plane, if there's something like this, solar probe will be measured very different plasma at different locations, and that's why it's really important to identify what we are measuring from solar probe, because we simply don't know. So this is the main mission objective of solar probe. We have 3 primary objectives.
You can skip to those.
I'm not going to skip. Yeah, I'm not going to skip. So I'm going to talk. So there are 3 primary objectives. One is to trace the flow of energy that heats the solar corona and accelerate the solar wind.
We'd like to hear the thesis objectives.
Yeah, it's in the next slide.
Okay, let's go there.
Yeah. So in this thesis, I'm going to partially address 3 of the sub-objectives from solar probe. First is how the energy from solar atmosphere will be transferred and dissipated in the corona and solar wind. And also, how does the magnetic field in solar wind source regions connect to the photosphere and the heliosphere? And also, are the sources of solar wind steady or intermittent? So through this thesis, I would like to partially address this objective. And finally, reach this part of introduction. So in this part, I talk about MHD wave because one of my chapter here will be discuss the linear mode conversion of MHD wave. This is the fluid MHD equations. Basically, it's a fluid equation and combined with Maxwell equations, and assuming it's non-relativistic. That's why I can ignore the electric field. And if you solve this equation and linearize it, assuming that the perturbation is very small, you have a free velocity perturbation with 3 modes. One is Alfvén mode, fast mode, and slow mode. So this free velocity perturbation will form a orthogonal triad. They're orthogonal to each other. And the slow mode and fast mode will be on the plane defined by the wave vector and background with the magnetic field. And the Alfvén perturbation will be perpendicular to that. And this is the phase velocity diagram in different cases. When the Alfvén speed is smaller than sound speed, the fast mode will be more sonic-like. So it's very isotropic, and it's pretty much a normal sound wave. And when sound speed equal Alfvén speed, there's something interesting happening. The slow mode and fast mode will have an identity crisis. They don't know what they are, especially when the wave vector is parallel to the magnetic field. So they don't know what they are at this point. And similarly, it's symmetric for Alfvén speed larger than sound speed. But this is a very simple model, right? So small amplitude. It's what we call a spherical curve in vacuum. It's very ideal. So in reality, what does Alfvén wave looks like? It actually looks like this. Let's start. Oh. Gosh,
Is it a movie?
it's a movie.
Or you can maybe go down maybe there, it shows the bar.
No.
Maybe exit and show it as a movie from the outside the car.
Oh, haven't enabled it. Okay. Now I can see it. Okay, so this is what Alfvén wave actually looks like in the solar wind. Let's actually stop at some frame. So this is what we call a spherically polarized Alfvén wave. Come on. Where's my mouse? Where's my mouse here? So this is what we call a spherically polarized Alfvén wave. The black line here is the magnetic magnitude. The blue line here is the radial component of magnetic magnitude. So yeah, in this Cartesian coordinate system, PSP. And the green line is the radial component of the velocity field. You can see there's a remarkable similarity between the VR and ER. They are perfectly correlated, which indicates that they're Alfvén wave. However, the amplitude of this wave is really large. The magnitude here is 100 nanotesla, but the magnetic field can turn almost back, or in this case, almost to zero. In this case, which, however, still have the magnetic magnitude remains constant, which means it's a spherically polarized wave. So the magnetic vector basically rotating on a constant sphere, and this is what we call a spherically polarized Alfvén wave. And I will discuss this panel later in this presentation. So what is a spherically polarized Alfvén wave? So it's something like this. So you still have the background B0, and this is the actual magnetic field vector. The perturbation component is this B1. So the perturbation can actually reach from 0 to B0, and pretty large. When it's reached somewhere here, it's what people call a switchback. The scenario is something like this. Imagine that you are inside of a flux field of the open field line regions extending from corona base. Without any perturbation, the field line pretty much looks like this. But with the perturbation, the field line would be twisted downwards and upwards. So however complex it is, and it's still the same field line. How do people know this? So people in solar probe team, they look at the pitch angle distribution inside of a switchback and finds that it's always pointing to the same direction, actually always pointing outwards. That's how people know that it's the same field line, even though the magnetic field turns backwards and back. So this is a qualitative illustration of what a spherically polarized Alfvén wave is, and still making the magnetic magnitude constant. Okay, finally, discuss turbulence. So what is turbulence? Turbulence is something like this. Something that you cannot predict, basically. You have eddies from large scale to small scales everywhere. But, okay, so how does turbulence happen? You can see that if, suppose this fluid will have almost zero viscosity and still have a constant energy input, the fluid will, from observational results, that will find a way to dissipate the energy at some point. However, the dissipation term here, which is this is a kinetic viscosity, will be nu times the lambda squared u. If you Fourier transform that, it's proportional to k squared. So the viscosity is only significant for large k, which means small enough scales. But the energy is being injected to the system at large scales. So the system will find a way to transport the energy from large scale to small scale without losing any energy or without depositing any energy in the intermediate scale. And just a very famous mathematician whose name is Kolmogorov in the 1941 and derived that using this phenomenology and derived that if this happens, the energy do not lose from in the intermediate scale. The power spectrum density of this velocity perturbation would look like pk proportional to k to the negative 5/1. And that's usual fluid turbulence, right? So in reality, or in the turbulence I measured in solar wind, this is what we call solar wind turbulence. So in solar wind, usually use the magnetic field to study a turbulence because magnetic field will have a higher temporal resolution. This is a free component of the magnetic field measured in the near Earth solar wind in the 1971. So after all this large amplitude fluctuation in the magnetic field, and it's almost perfectly correlated with the velocity perturbation. So these are bandwidths basically. So what is a solar wind turbulence? This is a standard model solar wind turbulence. So you in the low frequency range or the energy injection range or energy containing range, whatever you call it, usually have this 1/f scaling. And in the inertial range, you have this -5 scaling, sometimes smaller. Depends on what phenomenology you're going to interpret that. And there's a radial evolution of the solar wind turbulence spectrum. So as when you are very close to the sun, looks like 1/f. In low frequency, you have an inertial range at high frequency, and the energy level goes down with increasing heliocentric distance due to the WKB effect. And the break point between the low frequency range and the inertial range between the low frequency and inertial range, we move to lower and lower frequency with increasing heliocentric distance, especially for the fast wind. This is the solar wind that is originating from the coronal holes. However, in this thesis, I'm not going to discuss a lot of things in inertial range. I will be most primarily focused on the energy injection range because it's simpler. Okay, what is the energy containing 1/f range? It's actually pretty simple. If the scaling is 1/f, f to the -1, if you integrate that, you get log f2 divided by f1. So for the same frequency range in the logarithmic scale, for example, we have 2f divided by f, it contains the same amount of energy regardless what f you're choosing. So whatever frequency you're choosing, it contains the same amount of energy around you. So the energy distributes evenly across different scales. And this 1/f range is actually pretty famous. It has been proposed by numerous models to explain why there is such a 1/f range in the solar wind turbulence with so many theories over the past 4 decades. We're trying to address some of this in this thesis. Okay, finally, reach my own study. So let's try to understand. So because solar probe is moving so quickly in the perihelion, but this is the PSP orbit design again. Each of these dots is plotted daily. So from here to here is 24 hours. You can see here at perihelion, solar probe can move more than 60 degrees in Carrington longitude within 1 day. So it's moving extremely quickly. That means especially in the co-rotating frame. That being said, the probe can be measuring very, very different things over an extended period of time. So we can measure the solar wind from one coronal hole and another coronal hole, and then here's the occurrence here. So it makes it very important to understand or to contextualize what we are measuring using solar probe data. And this is, for example, this is one extended coronal hole for encounter 10 that is determined using the potential field source surface modeling. Well, what is the potential field source surface modeling? A potential, so it's called PFSS. So it's a technique which assumes that there's a source surface somewhere, usually at 2.5 solar radii above from the solar surface, and assumes that at the source surface, all the field lines are purely radial. And then you can, with that as a boundary condition, you can integrate the magnetic field from the solar surface using magnetogram from, for example, SOHO HMI instrument that can measure the magnetic field remotely on the solar surface, and then can integrate this magnetic field line from the solar surface to the source surface. With that, you can kind of see what is a magnetic structure from solar surface to infinity. So you have this open field lines here, and you have this closed field line, and you can also determine its polarity. And then for solar probe case, what we really care about is the magnetic connectivity of the magnetic field to the solar surface in the ecliptic plane, because as I showed above, the solar probe is pretty much in the ecliptic plane, it's not moving in latitude. Okay, so what people really do to connect the magnetic field measurement at solar probe to the solar surface is through this. So the solar surface is at 2.5 solar radii, and solar probe is somewhere here, 10 solar radii, to elastically project the solar probe location to the solar surface and then back to the solar surface. And with this, people have achieved some very impressive thing. For example, this is encounter 10. So in PSP encounter 10, people found that from November the 17th to November 20th, for 3 days, all the magnetic field can be actually connected to a single coronal hole at mid-magnitude. And then the next day, connect to another coronal hole, and then the next day, connect to another coronal hole. And this is the Alfvén Mach number over the orbit of PSP. However, this method contains some defects, as we discussed above. The solar surface is actually arbitrary, and there are lots of parameters you can play with, which will create very different results with small difference in initial condition. So what can we do with solar probe data only? How about just staring at the time series and see whether we can find some characteristics from the time series only? So I will usually say this, observation is all you need. So let's start from a simple observation. This is always a solar probe. What you do, you choose an interval and you plot the magnitude, the magnetic field with regard to heliocentric distance. And then you plot this with a log-log diagram. You see, oh, very surprised. The magnitude actually trends almost perfectly with heliocentric distance, with a power law index of negative 1.86. And the next step, you plot the magnetic magnitude, you plot the distribution of it, the histogram. So the raw data here will create a histogram like this. However, if you normalize with this helio-radial power law field, it will almost miraculously turns this histogram into something like a delta function. This blue histogram here is the raw data, and the red histogram here is the normalized data. So it's normalized with this power law field, and S is 1.86. And you can expand that, and really surprisingly, this thing looks pretty much a Gaussian. So what you do, you overplot a Gaussian, and see, it really looks like a Gaussian. Then maybe you can think of one method to quantify how Gaussian it is. And there's this very useful method in statistics, which will calculate the statistical distance between one distribution function, the red one, and the other reference distribution function, which is the Gaussian, and calculate how different they are. And it's called the Zesen distance. It's a statistical distance between two distribution functions. So with that, we calculate the distance of this red thing and the Gaussian to be 10 to the negative 1.43. Pretty small. So the smaller distance, the more similar they are. So the whole process actually creates two parameters, right? One is this helio-radial power law field, because I choose the interval and then I fit that, and I call that alpha. And the other is the Gaussianity of it, how Gaussian the normalized magnetic field can be. So the whole process creates two parameters that is dependent on the location of the interval and the size of the interval, because I can always select this window and choose different window sizes. So it's a 2D dependence. So with that, we can do one very simple thing. How about select all the data with all different window sizes and create all of these values? What do we get?
Oh, so the fit is done to optimize those both parameters, or just the first parameter?
It's a simple fit. Just plot the magnitude with R and just fit.
Oh,
yeah.
Oh, and then you derive the stroke.
Yeah. Based on this fit. So
you might want to comment on the fact that someone might expect mod B to scale like R to the -2.
Oh. Yeah.
And what's the significance of the 1.8?
Why is it? Why do you have any idea as to why it's less than 2? Or
supposedly the flux tube is expanding radially as a flux tube. A radial expansion will produce a Given radial power law dependent on R to -2 because the surface increase R to -2. But in reality, we find, well, I will later show that this value is very close to this value, regardless of location in the.
But this is the magnitude, right?
Yeah, magnitude.
Not the radial.
Not the radial component.
Yes, not the radial components, but as we can see in the few slides ago.
The B5 drops off as a different scale, so 1/r.
Yes, but you see BR here, the envelope of BR is actually B magnitude. So BR is itself is doing something like this. So B magnitude is basically BR at sortable distance.
Because it's mostly radial there. Because the field is mostly radial.
Yeah, because field mostly radial when perturbation is absent. With the presence of perturbation, you create this.
Yeah, so I remember in one of the earlier presentations, I actually asked you this question. If you do the statistics on BR itself, do you get the same result?
I cannot because there's so large of a fluctuation.
Well, I understand there are like, you got like switchbacks and all that stuff.
Yeah,
I didn't understand why you cannot.
Because the fluctuation is too large. You have 100, 0, negative. You cannot fit this, or you can fit this up. I mean, you can fit the magnitude of BR. Yes, but I think it's more sensible to fit the envelope BR, which is more fit. That's why. So
what you're saying is that the noise on BR would be much bigger than the noise on mod B. If you show the plot of mod B as a function of distance. You showed it the next slide, or next two slides or something.
Yeah.
So there, the noise that you would have on that diagram would be much bigger, is what you're saying.
If the BR is something like this, it will fluctuate between positive and negative. Do that. Well, actually, someone else do that, so didn't do that myself. So with that, these two parameters will have a dependence on both location and window size. So we can create a diagram to visualize that. So how do I create this diagram? I choose the step size in T to be half the step size in window size, such that the temporal coverage of the single point, which means the window size, will be the same temporal coverage of 3 points in the following line and 5 points in the following line, and all the way to the smallest window size. So if all of these intervals have similar properties, for example, how Gaussian is, it will have similar colors for all of these points because they cover in the same temporal range. So you expect that if something has similar properties, it will have something, this pyramid structure. So what do we see? Here on the upper panel is the radial, is the alpha, which is helio-radial power law fit index, plotted with different window size and location. You can see regardless of location, and this diagram here, the color bar is choose such that, so white color is R to -2 because that's expected. And regardless of location and scales, it's pretty much smaller than -2. And that's very interesting. It's very simple. That's first discovery. And second discovery is that this diagram shows the Gaussian energy as a function of scale and location. You can see all this pyramid structure here. What does it mean? From previous slides, you can see that it means that regardless of location and scale, from November 17th to November 21st, the magnitude is Gaussian everywhere, regardless at any location and any scales above 7 hours. So maybe we can do this. We can find the local minimum of the Gaussian energy. Oh, what's the sound? Okay. So we can do one thing. We can find the local minimum of the Gaussian energy, the most Gaussian place at the different scales and location, which means at that location is very Gaussian. And it covers the time range from November the 17th to November the 20th, which actually coincides with the coronal hole. found in the other paper. So they found that the coronal hole extends from November the 17th to November the 20th, just from here to here. You see a white pyramid. And then you see a very dark region here. And then the next day, for the 16 hours in the November the 21st, you see another small pyramid structures. Well, at this point, I also find it with the local minimum, with a restriction of the window size. So there's two pyramids here. And this pyramid happened to correspond with this part that's connected to the coronal hole. And this part connects to another coronal hole here, which is kind of interesting. So what can we do next? This corresponds to this, it's in fast wind, that's why it's coronal hole, and this corresponds to this, it's also fast wind. So what can we do next? How about study other intervals that find some coronal holes that no one has ever found before? This is encounter 12. You can see it's really white, which is really Gaussian, regardless of location and scales. And maybe you can find the local minimum again. And we do a PFSS using this as a prediction. And we see, in fact, really, from May the 27th to the whole day of May the 31st is another mid-negative coronal hole. So this method can be used reversely to find coronal holes from in situ data. And this is especially important because our hole is moving so quickly in longitude that we really need this method to identify what structures we are seeing in the solar wind.
It's a validation also.
Yeah.
Assessment in a sense.
Yes, and it can also use as a method to find the actual boundary because PFSS can, as you can see here, is usually produce data once per day. But this we can find a sharp boundary between the coronal hole and non-coronal region.
Please just remind me of one thing. So at the top is the middle panel is the measure of degree of Gaussianity, and the bottom, please remind me what the arc is.
I can go back here. It's the field index between the magnitude and the heliocentric distance.
Yes.
There's a function of different scale and location. Okay, so this is one application of this method. How about we apply this method to smaller scales? Oh, by the way, so for this coronal hole, with the power of it, this is extremely clean, and it will turn the distribution of mod B into almost a delta function like thing. It's very, very good. I will discuss about this in later slides, why it's Gaussian and why it's very constant. So we can first apply this method to larger scale, for example, using Ulysses data. So this is the first orbit of Ulysses, and we can do the same thing, that calculate the Gaussianity at different scale and location. You can see this two pyramid here, and this boundary here is artificial. It's an arbitrary effect because the Ulysses is not moving that quickly in radial distance. So I have to set a hard boundary whether I'm going to apply the helio-radial power law fit or not. So for the short intervals, I do not apply the helio-radial power law fit. For longer video, for longer interval, I do that. So here, if the largest radial distance divided by small radial distance is smaller than 1.5, I do not apply the helio-radial power law fit before passing to the Gaussianity test. Above that, I normalize it and pass the Gaussianity test. That's why you can see a boundary here. But nevertheless, you can see two very wide pyramid here. What they are? What are they? So this diagram here, this line here is the latitude of the Ulysses, and colored with local solar wind speed. So as Ulysses reaches southern polar, gets into the polar coronal hole with fast wind, you see this. As it reaches northern polar, goes to northern polar hole with fast wind, we see this. That means these two are polar coronal holes. That's another application of this method. You can find polar coronal holes, which is interesting. In addition to that, we can apply this method to smaller scales, in hour scales. At different locations, we find all of the structures that spanning everywhere looks like fractal structures, but I don't know whether they're fractal or not. And it has some decent correspondence to the so-called switchback patches. For example, from here, you see no switchback actually here. And there's a patch of switchback. That's what people call the switchback patches in solar wind community. And this method has some okay correspondence with them, not like perfect. And we can apply this method to even smaller scales. So this is the encountered 12 coronal hole that I found earlier. And we can find the Gaussianity structures at various different scales. So this is larger scales that you have a coronal hole here, and which to smaller, from 0 to 48 hours, you see a lot of the structures. And go to even smaller scales. Do you see? Go to even smaller scales, we see there are more structures here. How about go to smaller scales? What do we see? We see all of this really intermittent and very clear boundary structures, and numerous structures that has extremely clear boundaries at the smaller scales that has several minutes long. So that being said, probably based on this, we can claim that the solar wind at its source is really intermittent, because we have all this coherent structure based on the Gaussianity of the magnetic magnitude. The most remarkable thing is that all of the structures is actually compiled from this line, this black line here. It's seemingly featureless, right? If you just look at this diagram here. It doesn't have any features, the black line, but you can still extract a lot of information from the seemingly featureless line here. So this is one of the most interesting discovery I use this method, is that we found this universal 1-minute structures everywhere in the sun. By everywhere, it's because it's really everywhere. So let's go back to the video I showed earlier at the very beginning slides. You see all these structures everywhere in the wind. And we don't know what they are, because I stopped my study here. Haven't continued yet. Okay, so let's move on.
Can I ask a quick question? So in all the analysis, the time is the observational time, means the time is in the spacecraft, right?
Yes. Yes.
Have you tried to say convert it to the solar frame?
I haven't yet. Actually, there's some indication here. This panel is the longitude plotted every 1 degree. So this is used to indicate how large the size of the what is the size of this thing. For example, here this thing has 2 Kelvin longitude in size. But I haven't do a really transformation yet. But yeah. By the way, so this interesting here could be the plume you see in the wind, because as you see earlier, SOLPRO is actually measuring the plume in situ, but we don't know yet. That's one of the
suggestion from Hao is very important, because that linear axis is transformed essentially in a nonlinear way, because the speed of the spacecraft is changing dramatically throughout the orbit from the radial scan to the knot. So some of those regions are going to be broadly expanded, and some of them are going to be squished together depending on the direction in which the spacecraft is going. And so maybe there's something to learn from there, which would be useful to plot.
Yeah, I really agree. I agree with that. Yes, I think this is a very important next step on the study. Okay, so finally, for the final part of the study, why the solar wind has this Gaussian structure anyway? So we did a 3D simulation with a 3D box. We initialized the box with a linearly polarized Alfvén wave. Therefore, at time equals 0, the distribution of mod B looks like this. Why it looks like this? Because we have a strong background field, and because the Alfvén wave is linearly polarized, the perturbation is perpendicular to B0. So it will only add perturbation on top of the B0 here. So it looks like this to begin with in the Alfvénic turbulence setup. And if we let the simulation run, the Gaussian, this thing, will quickly become a Gaussian within one nonlinear time in the system, which is the linear time of the system is defined by the size of the box divided by the Alfvén wave, how long it takes for the Alfvén wave packet to pass from the one side of the box to the other. So it reached Gaussian within one nonlinear time, which means that, well, actually half of that nonlinear time, which means it takes only the time for the Alfvén wave to propagate from one side of the box to the center of the box to make the distribution of mod B become Gaussian. And this is the Gaussianity of this thing. It's not very Gaussian to begin with, and then become very Gaussian as time goes. And this is how it looks like. as a function of time, so it becomes very Gaussian very quickly. So maybe Gaussian distribution is a natural relaxation state for an Alfvénic turbulence. That's one of the conclusions, but this is one of the future study I will discuss. However, this can only account for the minutes-long structures because they have causality relations. For the interval, for the interval that are several days long, for example, the corona hole that's several days long, the information cannot propagate from this side of corona hole to the other, because there is no perpendicular information carrier, because the solar wind is at corona at solar probe distance, the plasma beta is very small, so compressible wave will be rapidly damped. And solar wind is very Alfvénic, so most of the energy is in the Alfvén waves. So there's no reason that information can propagate from here to here for the whole corona hole. So what's happening? Why is Gaussian to begin with? This is a simple, really simple model. Imagine that there is no perturbation in the flux tube. And because the plasma beta is very small, so you have a pressure balance with magnetic field only for the same cross section of a flux tube. So for any place in this cross section, the magnetic pressure is the same everywhere, because if it's not the same, it will quickly dissipate due to the pressure balance. And if you introduce some perturbation, the polarization is superiorly polarized. It will not change the magnetic magnitude at all. Maybe small, a little bit, but not that much. And therefore, you would expect that for the same cross section of the flux tube, you have the same magnetic magnitude. And then you're going to add noise to this. How will the noise look like? I would imagine that the noise will be some stochastic process that we don't know, but it will be additive in nature. So one plasma parcel here will have some noise, kick the magnetic magnitude upwards and downwards with some mysterious stochastic process. But it's additive in nature, and therefore, due to central limit theorem, at solar probe distance for the same cross section, it will be Gaussian. It's a natural process. It's a natural process due to central limit theorem. So the solar probe, as it passes through a flux tube in the corona hole, the helio-radial power of it that I did earlier is actually mapping all of this measurement at different radial distance back to the same cross section. That's why you see a very, very constant normalized magnetic magnitude. It's almost like a delta function. And then the Gaussian is actually the noise in the magnetic magnitude.
Is the thickness of the Gaussian, the width of the Gaussian correlated with something like plasma beta or something?
I haven't really studied that.
Be worth looking into that.
Yeah.
Can tease out more information.
I think so. Thanks. That's a very good comment. Okay, finally, we finished this part. This one paper that I have.
You're going to have to accelerate a little bit.
Okay, I want to accelerate. So this is the second part of my own work. It contains 3 parts. So we call it Alfvén and turbulence in the heliosphere. So first, we begin to understand the MHD mode conversion in the system. So the sun will have a 5-minute oscillation that is trapped between the photosphere and the tachocline, because it's excited at the surface with solar granulation, and all this fluctuation is trapped within this resonance chamber, and therefore it's a very classical observation that all the fluctuation energy is concentrated at around 3,000 μHz, which is 5 minutes. This is a very classical 5 minutes p-mode oscillation from the solar surface. So all fluctuation concentrated around 5 minutes on the sun. However, the real situation of the sun is so complex. It's really complex, but and this is a modernized picture of the solar chromosphere. The takeaway point here is that in the photosphere, the plasma beta is very large, usually outside of the active region. And in the corona, the plasma beta is very small because magnetic field dominates. So somewhere in the chromosphere, there's a layer where the plasma beta becomes 1. That being said, the sound speed equal Alfvén speed. And people propose that there will be a linear mode conversion from the P mode, which is acoustic in nature, and becomes the fast mode above, which is magnetic in nature, due to linear mode conversion at this layer where the sound speed equal Alfvén speed, where people call the magnetic canopy. Does that really happen? So here, in our study, we do a simple 1D simulation with expanding box model to see whether this linear mode conversion actually happens. So in expanding box model, as you propagate outwards, the background magnetic field will turn away from the radio due to expansion, and the wave vector will turn towards the radio also due to expansion. So somewhere in the middle, the B0 will be aligned with K, and if we choose the initial condition carefully, we can make such that when the B0 and K is parallel, the sound speed also equal Alfvén speed, so that we can create a linear mode conversion condition for that. So, however, how to quantify the mode conversion anyway? There's a very classical way to do that using an adiabatic invariant of the wave. So there's a conservation of wave action density in the wave. So what's the wave action? Wave action is the energy density of the wave divided by its own frequency. If you remember in quantum mechanics, what is that? This energy divided frequency is the wave quanta. So when the wave frequency is much larger than the characteristic frequency of the system, the wave quanta is an adiabatic invariant. So we can use that to quantify the wave action of 3 different modes, because actually there's a minus sign here, so we have to change that. Because the Lagrangian of this wave is L equal to this, it's kinetic energy divided by the compressive energy and minus the magnetic energy. It's always equal to 0, even though you cannot decompose this part of the energy. But you can decompose this part of energy because US, UN, UF forms the orthogonal triad. Here, they are decomposable from each other. So we can calculate the velocity perturbation here and project on each of the axes in the orthogonal triad to calculate the wave action for each mode. Therefore, this is what we do. We initialize the system with linearly polarized fast wave here. It's all green because it's a normalized wave action, so it's 100% fast mode or green. And then as it passes through the region, so this bar here indicates that the wave vector parallel to B0. And this region here indicates that the sound speed equal Alfvén. So as it passes through this region, the fast mode will be partially converted to slow mode here in orange due to linear mode conversion. And still, the total wave action of both modes remains constant. So that's one of the findings on my paper, that the linear mode conversion actually conserves total wave action of 3 MHD mode. So why does this happen? This red dashed line here shows the polarization of different velocity and magnitude components at this time. You can see that the velocity perturbation here, which is in one period, which is this black dashed line, is something like this. It's parallel to the fast mode polarization. So if you project this very thin this, you see that it's almost 100% fast mode at this point. That's why it's all green. And at this point, the velocity perturbation becomes a very bad ellipse. Therefore, you have projection on both fast mode and slow mode. Therefore, you have 25% of slow mode and 75% of fast mode. That's a linear conversion between both modes. Why does that actually happen? So we can look at the plasma beta here. When plasma beta become very close to when plasma beta become very close to 1, the UF and US will have a sudden change in this direction. However, the velocity perturbation do not know this information. So at that point, this velocity perturbation will have an identity crisis. The velocity doesn't know what they are. So after the sudden change of the polarization change, it will have a new perturbation. You have a new projection on each of the eigenmodes. Okay, so this is a linear mode conversion. Finally, let's reach the interesting part of this talk. So the observation of 1 over average in PSP data and 3 minutes oscillation of corona. Okay. So the standard Soloway model is like this. You have 1 over average in low frequency range, right? But is that really the case? So in my paper in 2023, we found that oh, surprisingly, 1 range actually disappeared when solar probe is very close to the sun. The low frequency of the spectrum actually scales like f to the negative 0.6 for this interval. There's no 1 range at all. But in fact, this is not really new. They found a Helios data in the 70s and been found here. So this is one single interval. I think people have found prior to solar probe launch. This interval is at 0.3 solar radii, and all of this interval found by solar probe below 0.3 solar radii reveal that this is the dominant case, that we don't have the 1 range very close to the sun.
Zesen, can I ask a question? Right? In the intro you showed, that was using data mostly at 1A.
Yeah.
And also these observatories don't move in radio. You don't have much radio movement.
Yes.
In your data analysis, your spacecraft actually has a radio movement.
Yeah, I will discuss that in following slides. That's actually a very important thing to clarify. But before that, let's discuss what does this really mean. Okay. So when the spectrum is shallower than 1 f here, why it's shallower? Because if I compensate the spectrum with f, it's going up. That's why it's shallower 1 f in this range. And compensate the spectrum with f, it will be like this. So this part is shallower 1 f, this part is steeper than 1 f. As I discussed earlier, 1 f means that the energy distributes evenly across the scales in the spectrum. That being said, when the spectrum is shallower than 1 f, the higher the frequency, the more energetic the spectrum is. When the spectrum is steeper than 1 f, the lower the frequency, the more energetic the spectrum is. That being said, most of the energy actually contains in this band, in the spectrum. To prove that, we can integrate the spectrum from high frequency to low frequency. And this dotted dashed line is the normalized energy of the spectrum. So from here, integrate. This means that from here to here, this part of the spectrum contains 25% of the energy of the spectrum. And from here to here, the small frequency band contains 25% to 75% of energy of the spectrum. From here to here, contains another 25%. That being said, this small frequency band here contains 50% of total fluctuating energy of the spectrum. That actually means something.
Well, the dashed line is basically energy per fixed unit frequency. That's all. So you can just show the peak and say that's where the energy is, as you did.
Yes. I didn't know that terminology. Yes, that's what I'm trying to say. Okay. So, however, as we said, solar probe is moving quickly in a solar frame. So there's a Doppler shift here, actually. So how to interpret the frequency spectrum that we see from solar probe? Let's imagine that we're going to shoot some wave at the corona base, which is on the solar inertial frame. Okay, and there's another frequency in a plasma frame, which I call F1. From the point of view of the plasma, the source of the wave, which is the corona base, is moving away from itself at the speed of u. Therefore, in a plasma frame, the frequency is actually Doppler shifted downwards to this. So F1 is F0 times VA divided by U plus VA, because the source is moving away from the observer. And it will be Doppler shifted again back to the solar probe frame. Let's assume that the solar probe is not moving at all. From the point of view of the sun, that is stable. That's most of the case in 1AU. This is 0, so F is actually equal to F0, and solar probe is not moving because they're basically in the same frame. However, if solar probe is moving in, and this is positive, the frequency will be Doppler shifted to higher frequency if solar probe is moving inward. However, the phase velocity of the wave is U plus VA, is usually is usually at the scale of 1,000 kilometers a second as solar probe distance, but the maximum radial speed of solar probe it can reach is only 100 kilometers per second. So from the radial point of view, the frequency spectrum measured by solar probe is actually the real frequency spectrum that's launched at the corona base, assuming that nonlinear effect is not important, which I will discuss why it's not important later. But if there's no nonlinear effect, and this is actually true, the frequency spectrum we see as solar probe is the actual frequency spectrum that's launched at the corona base. So let's look at one example.
10%. 10% there.
Yeah, up to 10% difference. Let's look at one of this interval here. This is the interval that I showed earlier. You can see here, solar probe actually moving very quickly for this interval. This interval is 6 hours. Well, the most of the movement is actually in the parallel direction, which is more significant. But let's forget about it. So this interval here, why is really interesting? Because first of all, it's sub-Alfvénic. Why? So this blue line here is the Alfvén speed, and the green line here is the local radial solar wind speed. In the middle of the interval, the Alfvén speed overtakes the local solar wind speed, so it becomes sub-Alfvénic here. This is also shown with this red line. The red line is R times the Alfvén Mach number. When it dips below the real radial distance of the probe, it becomes sub-Alfvénic. So it's super Alfvénic in the beginning of the interval, because sub-Alfvénic final part of the interval. And also, this interval is very Alfvénic. That being said, all of the fluctuations are actually Alfvén wave. And it's very low plus of beta. It has small advection time. The advection time is only 7 hours. And something also interesting is that if you see here the energy as we concentrate around 3 minutes, the actual physical carrier of all of this fluctuation power is actually what we call the switchback, because by definition, the switchback is the largest amplitude fluctuation in the solar wind. So the switchback is this radial reversal of magnetic field, and also you can see in the jets because they're hour propagated. So the physical carrier of this energy is actually the switchback. Here I show more interval here that also characterized by this double shallow inertial double power law. The energy, all of this energy concentrated, 50% energy concentrated around this green band for all intervals. So 50%, 50%, 50%, 50%. Okay. So what do we do? With this, let's go back here. So because this frequency band here contains 50% of fluctuation energy, we can use this to define the frequency as a primary fluctuation frequency of this interval, which is the middle of this green band. In this case, it's 148 seconds. It's somewhere between 2 minutes and 3 minutes. With that, we can do a radial analysis of all solar probe data using this parameter here. What do we see? So here I scan all data from encounter 1 to encounter 17 of solar probe data, and I plot the primary fluctuation frequency in temporal scale, in temporal units, as a function of advection time, which is the radial distance divided by the local solar wind speed, which can be used as a proxy to the age of the turbulence. Right? The smaller this time is, the younger the wind is, basically. So as the wind becomes younger, this primary fluctuation frequency will perfectly drift to somewhere in 3 minutes for the youngest wind. And using the Gaussianity method that I discussed in previous chapter, we can actually filter all this interval and only use those intervals that has a high Gaussianity, which I think they are originating from corona holes, if you believe that. So if I use a general distance filtering, that's a criteria of 0.1. A smaller point means that it's very Gaussian. It will filter out all of this heliospheric coefficient crossing the C and E, because those will destroy the Gaussianity of the magnetic magnitude. You see an even clearer trend that this thing will drift towards 3 minutes. And if you follow the 2 corona holes that I discussed in the previous chapter, this is the 10F mid for following the same corona hole. If it goes down, and maybe up a bit, but it will stabilize around here for the youngest wind. Okay, so this is a primary result here. What does it mean? First of all, the advection time itself is actually not a good indicator of the age of the wave, because the Alfvén speed from corona base to the probe to solar probe distance is actually pretty big. usually the Alfvén speed will start from 2,000 or even 4,000 kilometers at the coronal base and reach about 500 kilometers at the Alfvén surface. That being said, the phase velocity, which is VA plus U, is almost always bigger than 1,000 kilometers per second from coronal base to solar probe distance. So the real propagation time of the wave is actually less than 2 hours. It's really small. Let's see what 2 hours can do to this 108 mid. So from here to here, if 2 hours, you will only drift this thing by 1 minute. But that's only an estimation because the fact that this 108 mid is moving to lower frequency is an indication of the active turbulence cascade and dissipation in the solar wind. The reason why this primary fluctuation frequency drifts to lower frequency is because the energy is constantly being injected in the energy injection scale, being dissipated in energy dissipation scale. And it will eat some of the energy and move the frequency to lower frequency. And therefore, if this wave is being emitted at the coronal base, maybe 2 hours is not enough to change the frequency spectrum significantly. And also, there's another problem though. Are these really Alfvén wave? We need to really figure out the transmission coefficient of the Alfvén wave from coronal base to solar probe distance. So here I do a very simple analysis using Wei 1993 linear propagation model. So this is an Alfvén speed profile. You have to start from 2,000 kilometers per second, and you create a Alfvén surface at around 15 solar radii, which is informed by observation. So using this solar wind speed and Alfvén speed profile, the transmission coefficient for 3 minutes wave is 99.7%. So it's almost perfect. So we're pretty safe that they're Alfvén wave. And finally, why 3 minutes? Because, as we discussed above, at the photosphere, the fluctuation frequency is about 5 minutes. As it goes in the chromosphere, there's a very classical observation that the frequency will drift from 5 minutes to 3 minutes. So the primary fluctuation mode in chromosphere is 3 minutes. And that could be the energy source of what the Alfvén wave that we see in the solar wind. Because it's a forced oscillation. That's a simple explanation. And also, you can see that the 108 range is actually being formed in situ. This is a video just to show that what is actually happening, because all of these are statistics. You can see what is actually happening as you get close to the sun. The interval here, the power spectrum is here. You can see that you can find the 108 range using the compensated spectrum. When it's flat, it's 108. You see there's a 108 here. Okay, when you're far away from the sun, as you get close to the sun, closer, you will have you'll become the double power law that show. Almost there, come on. Playback, come on. Forget about it, let's jump a bit. See here, as we get close to the sun, this thing becomes more and more double power law, as I showed earlier. So there's a radial evolution of this thing.
0.3 was the distance, or the sweet spot where it transitions?
Transition is 0.15. So
very close.
Very close, about 20 solar radii. Like 0.1 solar radii. 0.1 AU, so it's 20 solar radii. Yeah. Okay. Finally, here's the conclusion. First conclusion is that the Gaussianity of B serves as a good parameter to identify structure in solar wind, as I showed earlier. It's really fascinating. And we found all of these structures from this method. You see coronal holes, switchback patches, many non-coherent structures. And also, the Alfvén waves are likely originating from the solar convection zone resonance chamber, which creates a 5 minutes oscillation. It's going to be leaked into the chromosphere, become 3 minutes oscillation. And probably this wave would be leaked into solar wind as 3 minutes oscillation. That's why we see 3 minutes oscillation in the solar wind. And the 1/F energy containing range will be dynamically created as the solar wind propagated outwards. And finally, these are the future works. First of all, why there's a Gaussianity in MHD turbulence? That's something really interesting. Actually, At least I didn't expect that. So if the Gaussian distribution is a natural relaxation state for magnetic magnitude, under what conditions this is true? We can do a parameter study of this and maybe do several more simulation as Professor Huang actually suggested me to do a longer box to see whether it's because of the propagation of fast move, which will create the relaxation of magnetic magnitude. Also, what is original, this very famous mono averages of in turbulence, maybe more detailed analysis can put constraints on different formation mechanisms, especially parametric decay instability, which I think is very interesting. Also, what is the origin of the shuttle after -5 range? Is it a direct effect of solar surface fluctuation? No one really studied that yet. Also, what's the implication of this thing? Can we use this 3 minutes oscillation as a constraint for the coronal heating mechanism? What does this 3 minutes oscillation tells us? That's also one thing to study. And that's all of my presentation. Sorry, it's really long. Any questions?
Do you want me to start? Okay, so perhaps one of the things that would be interesting to explore is the dynamic origin of not only the shift from 3 minutes. I think personally, I think the reason there's a shift from 5 minutes to 3 minutes is that the 5-minute oscillation is not really a delta function. There's a power spectrum, which is forcing. It has a peak at 5 minutes. Then the chromosphere is an oscillator that has a resonance at 3 minutes. And so most probably what happens is that the forcing, the maximum amplitude of the forcing is that, but it's a spectrum. So one immediate thing to do would be to try to use the best possible spectra that we have for the actual frequency oscillations, and then send those through a transmission profile and see if that might give origin to that f to the minus 0.5, which would be a fairly simple thing to do.
That's a very good suggestion.
Yeah. But the testing of the structures and the mod B Gaussianity is you claim that you can see the large coronal holes, phi, and then you claimed that you could identify some of the patches, but not all.
Yeah.
And then you claim that you could see smaller scale structures. Now, how would you test the quality of this identification? How would you go about trying to test the quality of this identification?
Well, my first thought is to, first of all, to label all the structures from data. As you can see from the video, there's so many of them, maybe tens or hundreds of thousands of them in data. First of all, is to identify them in the data and then use them to compare with the plasma products from solar probe, because I have never done that. For the reason I use this or invented this method is because the magnetic magnitude is really of high quality. There's little to no noise in that data. That's why I can use this method to identify these coherent structures. So that's the way to, I personally think the next step is to combine that with plasma product to see what's the correspondence between them.
Related to this part of the Gaussianity, I actually have a question, which is in the regions that are not Gaussian. Sorry if you commented on this and I missed this, but in regions where you see large departures from Gaussianity, how is it departing from Gaussianity?
Oh.
Is there anything of interest?
Yeah. I can go back. Here, the most significant structure is this, why it's all black, because it's a heater superior currency crossing. That's the first thing you can do. A heater superior currency crossing will create a large deviation from Gaussian because it's usually a large coronal, large magnetic hole. And also we can identify, for example, you see the peak here, that's also created non-Gaussianity in it. And it's also interesting say here, why there's a clear boundary between these two Gaussian structures? What creates this boundary? I did some preliminary analysis, and I think it's because of the existence of the second-law magnitude anomaly, what I call in a solar wind. So from here to here, the magnetic field is usually just a straight line with a little bit of Gaussian noise. But at this point, we will have a sudden fluctuation which separates these two Gaussian structures. But as to study what they are, that's really the next step. It also has developed an algorithm to identify them, but I haven't really going to study what they are.
But if you look at the distribution, what does it look like? Is it anything recognizable?
No, it's simple. So for example, here, if you there's a line interval here that have 5 minutes long that contains these two Gaussian, you have two peaks.
No, I'm talking about in the black region.
Yeah. Well, actually, that's what I.
Oh, sorry, then I misunderstood.
Yeah, yeah.
In the black region, you have two peaks. It looks like two Gaussians.
Yeah, because
modal distribution.
Yeah, because it contains part of this and contains part of
I
this.
see.
So
I see.
that's if he was very kind, she was very sorry, data plug, like different source searches.
Yeah, for this part, yes, you see.
So that's different?
This is minutes long. But this is very short.
Oh, very small, very small.
This is only
Yeah.
5 minutes long. Yeah. Yeah. So for this part, it will contain part of this Gaussian, part of this Gaussian. That's why.
Mixing two different
Yeah.
sources.
Yeah.
Question about the slope itself, right? You talked a lot about the Gaussianality on model, but going back to the slope themselves, I mean, I think in your next figure you showed the value of the slopes.
Yeah.
It seemed to go, not this one, I think here, right? It seems to go all the way from less than 1 to about 4.
Yes.
The R. Yeah, so I was just wondering, what do you think determines that slope?
Oh, okay. So for the smaller scales, I wouldn't trust the slope because the fluctuation itself is too large and the radial distance changes.
Yeah, you don't have much radial distance to give you, but for the big ones, right?
The big one is it's actually pretty interesting to see that it deviates significantly from 2 and become that stable. I would say it's an expansion factor of the flux tube that we see in the solar wind, but that's not really certain. Because this basically tells you that how this flux tube.
That's right. Yeah, so like the slope should be telling you how that particular slope, right? Flux tube expands.
Yes.
Right. If it's not expand spherically, right? If there are forces to squeeze it or expand in other ways, they will change it from 2. Right?
Yes, probably. Yes.
But again, remember it's the magnitude of B. So in fact, there are other effects that come into it. If you consider these to be Alfvén waves, then suppose that there is a process that continuously works to make mod B constant. I mean, if you imagine you throw fluctuations into a magnetic field, you would imagine that because you're propagating in a medium of lower and lower density, the amplitudes of the fluctuations will grow relative to the background. And there's no reason why a magnitude of B should really remain constant. It will try to develop, but clearly there are density fluctuations, something is going on with phase mixing or something that relaxes this to constant B. Now, why would that constant B go like -2? It no longer goes. BR would like to, if there were no wave-like phenomena, go like R to the -2. But the transverse components of B actually contain the elasticity of the Alfvén wave, and they behave differently. And so when you combine these two together, and the mechanism of constant mod B, it's actually quite natural to get a slope which is less than -2. Well, we could discuss that in more detail. But
just the natural expectation simply from the rotation of the sun and the deviation of the thin line from radial.
If it was dominated by very, very low frequencies, you would be right. But we're at frequencies about 3 minutes or so where the energy is. And so at those frequencies, there's also the coupling with the velocity field, which is relevant. So it changes it a little bit. So in other words, B transverse would go like 1/R, as you were saying, if it was completely static. But B transverse is coupled to U transverse. And so it actually decays a little bit faster than 1 over r. But if you combine this little bit faster than 1 over r with the 1 over r squared, it's just enough to get somewhere in between,
That's right.
which reduces it to less than -2.
Exactly, yeah. So you can determine that what the expectation simply from this is.
Yes,
And then it's the difference from that that you're
that's right.
trying to tease out.
So you may believe it or you may not believe it, but although I think this is fairly well known, there are people that are writing papers on this, but which contain information which is less than a blackboard worth of a little bit of algebra. But it's okay.
And that's another interesting effect I want to point out is that suppose there's no fluctuation, the field line density looks like this, right? If you introduce a switchback, it will kind of seemingly locally increase the field line density, which is magnitude, but it doesn't. Magnitude remains the same. So what probably really happens is that the existence of the switchback actually increase the size of the flux tree to maintain the same field line density. That's another effect that's possible. So the fluctuation itself can actually change the expansion factor. That's one of the possibilities that I think is interesting to point out.
These are elongated structures, so they have time to squeeze the field out.
Yes, we have time to relax this.
So last question on this, you've shown convincingly that you can go from fast to slow with the simple mechanisms here because the fluctuation polarization of the fast and slow are in the same plane.
Yes.
But we're invoking in P mode to P mode to chromospheric P mode to Alfvénic turbulence. You're invoking a transformation from fast to Alfvén. So can you say a few words? Because that's not really included in the calculation that you did. So,
yes, I didn't.
So how does that work? How do you think that works? Or what should we do to test whether it works?
So what I did is to show that this part actually works, but I didn't do this part. So what really happened in this double mode conversion proposed by these people in the past decade is that you start with a compressive fluctuation in the photosphere and become fast mode in the chromosphere. And because there's a steep Alfvén speed profile in the chromosphere, the fast mode will be refracted back like this. So this line is a ray tracing line to fast mode. But at the point of the refraction, the fast mode will linearly couple with Alfvén wave again. Well, not again. The linear couple with Alfvén wave at this point in a more than 1D ways. It's 3D in nature, so it will convert part of energy to the Alfvén wave eventually. But we haven't studied this part. I think this is also the next thing we should do to do a simulation to see whether this actually happens. But this needs a simulation more than 1D. The simulation that did is 1D. And this process is 3D in nature. And they claim that the whole double mode conversion process can transmit 30% of P mode in the corona, which is quite significant, which is 10%, 1,000% more than enough to power the solar wind.
Very interesting.
Okay.
We dismiss the.
So we can dismiss the audience and we.
I thought there was a question actually.
Oh, sure. One question.
Personal curious. So you mentioned about there's some scale invariant in this turbulent physics and the solar wind.
I mean,
I was wondering, so people like to use like renormalization group whenever they have scale invariance in lots of this kind of turbulent study of phase transition of physics, right? I mean, is that related to any of those and even to the question about your Gaussian distribution? Because sometimes when you zoom out and zoom in,
that's a great question. And as I showed in the following slides, the Gaussian, I think, the Gaussian that create this, the mechanism that create this Gaussian structure is different from the mechanism that create the large scale Gaussian structures. They may not be the real fractal thing because it's not really scale invariant.
Okay. But the physics at different scales still have some relation.
I think one of the difficulties in using renormalization group theory here is the coupling concept, which is large, not small.
So you cannot do it perturbatively.
It's not true because most loops doesn't converge. difficult. Although there have been attempts at doing renormalization on turbulent flow. There's a whole book, right? Jakob and Monin created some aspects of that. But they're by and large, not very successful, put it that way, because of the coupling constant.
But there is also an exact formulation about those, like exact renormalization group, like Hodgkin's, etc. That's kind of circumvent some of the pervasive difficulties.
That I know of in turbulent flow, maybe you can apply that. Maybe it's something worth exploring.
Should I dismiss the?
Any other questions from the audience or anyone from online? Questions? If not, okay. So let's